Hello to everyone and very welcome to our second webinar in the IETS Energy Transition series. My name is Oliver Lösch and I am the moderator for this webinar. Today we will be focusing on a very important and very relevant and very broad topic in industrial decarbonization, making better use of industrial waste heat. You can already see today's agenda on your screen. We have 3 exciting project presentations which cover a very wide range of applications and technologies, which illustrate the breadth of the topic of industrial excess heat recovery. First, we will start the event with a brief overview of the IETS TCP and Task 15 on industrial excess heat recovery of the IETS. Many thanks to all the speakers for their willingness to give insight into their projects to all of us today. Just a few organizational remarks at the start. After each presentation, there will be a short 5 minutes Q&A session. You can post your questions regarding the current presentation directly using the Teams Q&A function. Please do use only this Teams Q&A function and not the chat function of Teams. As the moderator, I will read out your questions after the presentations. Due to time constraints, it may not be possible in every case to address all of your questions. Please note that your camera and microphone is muted by default. If the speakers agree, the presentation slides will also be made available on the IETS website afterwards. Now let's go into it. I hand over to Per-Åke Frank from the IETS Secretariat for an introduction to the IETS TCP. Per-Åke, please go ahead.
Yes, hello everybody. I'm Per-Åke Frank from the Secretariat of Industrial Energy Related Technologies and System. Together with me at the Secretariat, Helen Johansson is also active. IETS is an IAA technology collaboration program, which is a global network for industrial collaboration. We have 12 member countries, you see the flags down to the left, and we have 4 sponsors. To be a sponsor is a way for an organization to join the network without being from a non-member country. The TCP are a unique network that brings together various groups to support energy efficiency and decarbonization. There are about 40 TCPs under IEE, and we are the only one focusing on industrial application. Our work is organized in tasks, and the tasks are either technology-oriented or system-oriented. For the moment, we have 9 tasks running. The oldest one is industrial-based biorefinery towards sustainability, which focus on integrated biorefineries, and ongoing work is to deliver decision support tools. Then we have the industrial excess heat, which René soon will go into details about. Then we come to a technology-oriented task, which is membrane processes in biorefineries, which the aim is to create biorefinery concepts utilizing membrane separation as a technology to produce biochemicals and biofuels. Then we have the digitalization and IE that aims to identify and develop these technologies to improve performance in energy and GHG intensive industry. In the electrification in industry task serves as a platform to exchange of information of ongoing project. The net zero industrial process in a circular economy framework aims to describe fossil-free industrial energy system. For the moment, a new subtask is starting, which focus on CCS technology. And then we have the climate resilience and energy adoption in industry under uncertainty and the primary aim is to promote understanding of climate resilience and energy adoption. And the 23 is drivers and barriers for the transformation of industrial energy system, which focus on non-technical aspects that are important for industrial transformation. And this is a joint initiative with Mission Innovation. And the last one, starting this year, is process integration for industrial decarbonization, which will create a model database to enhance the role of process integration. So what do you get when you join this collaboration? Well, you get direct communication with leading expert groups. You get synergy effect to avoid duplication of work, knowledge transfer, and access to report, webinars, and workshops, which is not possible if you're not a member of the task. You contribute by being an active participant, and you bring your already funded project, and you share your experience and results, and you participate in workshop, etc. All information is available at our website, where you have information of the task, publications, events, and other ongoing thing. To be updated, I would recommend you to join our newsletter, where you constantly, twice or three times a year, get information of what's going on. And here is the contact information if you need it. The chair from Johanna Mossberg, our vice chairs René from Austria, Lavinia from Switzerland, and the secretariat by myself and Helene Johansson. Thank you.
Thank you very much, Per-Åke, for this short, interesting introduction into the IETS TCP. I don't see any questions in our Q&A section, so I think we can go straight on, and I will hand over to René Hoffmann for a short introduction to task 15.
Thank you so much. Hello to everybody. My name is René Hoffmann. I'm with the TU Wien, a professor at the Institute of Energy Systems and Thermodynamics, and today I'm here responsible for the task 15, which is to industrial excess heat recovery. I'm the task manager, and together with all our colleagues and countries and participants, we try to answer a lot of questions. So this is a long-lasting task, means we are now in a structure which is the subtask 4. You can see we have a lot of interesting countries and participants, meaning we have 10 countries and 18 institutions, including university research institutes, consultants, and industry. Well, you can see here the structure of the task, meaning that we are already running to the end of our subtask 4. We have 3 activities, meaning we are looking in the role of excess heat in industry, we are looking on the strategic process integration, and we are looking also on ongoing projects at different TRL levels, giving a little bit knowledge transfer. So what does this mean? In the activity 1, there is the motivation about the industrial symbiosis, because that's not only industry itself, because this is a fruitful interaction between different sectors. We have demand response, domestic heating, power to heat, power to X, as you know it already. And the question is, this is a holistic system, and how our excess heat is also active if the system boundaries changes. The second is the activity about the avoiding log-in effects, because we know already a lot of different process integration methods, meaning we have the pinch analysis, we have also mathematical ways to do so. We know that there is a raw pinch analysis, meaning that we go first on estimation steps and then more in more detail. And this is very established. And the question is how to make those technologies or methods available for putting in new technologies into the systems by avoiding any effect which could be lasts in a login, meaning that if the system boundaries are changes, there is the question to be answered, okay, if we invest in a different technology, so what does it mean at the end? And then we have the activity 3, which means we have the systematic knowledge transfer, because a lot of projects, because this is a 10-year task from the starting point, we are now in the 3rd phase, meaning we in the subtask 4. That means there are a lot of different projects brought into this activity, and what we are doing, we try to develop a systematical knowledge transfer out of it. Yeah, the results are, we are developing a database. As you can see here in the activities, which are in colored shades, there are a lot of small written projects. It's not necessary to read them. They will all hopefully implemented in this platform to give a systematical view. We had a midterm meeting, which was with our industrial partner in ArcelorMittal in Messières. It was the last March, and there we had 2 workshops about the uncertainty and risk for strategic process integration and the introduction to new technologies and systems. So far, we have a lot of different achievements, meaning we had project sessions. Those project sessions are on the project level side, and you can find it on the YouTube channel, which is also available on the webpage, what Parker Frank has shown already at the IETS. And this we have also an ongoing survey where we are collecting the different projects into a database. And we are planning a workshop at the end, which it is in parallel with the 41th EXCO meeting in Vienna in November. Yes, this is it from my side. Thank you very much. If you have any questions, I'm happy to answer.
Thank you very much, René. I don't see actually any questions yet in our Q&A session, but everyone sees your contact data and can contact you afterwards. So we will now go over to our project presentations, and we will start with Paul Schwarzmeier, also from TU Wien, who will give us insights on their project 5D Industrial Twin. Paul, please go ahead.
Thank you very much. Hello, everyone. My name is Paul. I'm a senior researcher at TU Wien. And today I'm going to give you a quick insight into our projects that are related to waste heat recovery in the iron and steel industry. So the main reason we are doing this project, and probably also the main reason why you're all here today, are the 2 numbers on the left, which is on the top, the waste heat potential in the European Union, and on the bottom, the share of this whole potential that this actually puts to use afterwards, which is just 45%. And we are going to, at least we try to increase this percentage in the next few years. So the main reason why this percentage is so low can be structured in 3 main points, which is the fluctuating availability of excess heat, which makes it hard for most excess heat recovery systems to work in the optimal working point. Then there's also the mismatch between the availability of excess heat and the demand of process heat. So you have, most of the time, you have batch processes where you can't match those 2 things. And the last thing is, especially in industries like the iron and steel industry and the cement industry, that the excess heat mostly is contaminated with a lot of aggressive metal powder particles that destroy your waste heat recovery systems. So to give you kind of an idea what we mean by waste heat recovery. On this slide, you see a state-of-the-art waste heat recovery systems as we investigated it in our studies, which is just on the bottom left. You have an excess heat source, which is highly fluctuating. You have most of the time, half an hour, you have a lot of excess heat, and half an hour you don't have excess heat, and then this repeats afterwards. And yeah, this leads to a lot of exhaust gas losses after your steam generator, because those cannot follow this fluctuating excess heat availability. So what our plan is to integrate thermal storage systems into these excess heat or waste heat recovery systems to smoothen out this excess heat availability by storing half of the heat when it is available in the storage, and use this stored heat afterwards to close the gaps when no excess heat is available. So this way you can, yeah, as already mentioned, smoothen your excess heat profile, and therefore increase the utilization rate from initially 45% to theoretically 97% of the available heat. So before I jump into the details of our projects, I'm going to give you a quick heads up about the technology we're using. This technology is called packed bed thermal energy storage. It's quite simple. Basically, it's just a standing steel vessel. Most of the times it's cylindrical, and this is filled with a packed bed material, rocks, or in our case, we're using steel slag. Diameters of these particles are between 16 and 32 millimeters. Your storage vessel is filled with these particles, and the excess heat that you have available is inserted from the top. The gas flows in between the voids of your particles, transfers heat from the gas flow to the particles. The heat is stored in the particles, and the exhaust gases exit the storage on the bottom. So when discharging these storages, you just shift your thermocline from the bottom, or from the top to the bottom when you're charging it. And when you're discharging it, you're using cold air inserted from the bottom, pushing the thermocline to the top, and you can extract hot gases on the top when you need them. This is basically the information that you need for our technology. So what we did in our project 5D Industrial Twin the last 3 years is we investigated two main things to investigate the efficiency of these packed bed thermal energy storage for waste heat recovery in the iron and steel industry. The first part was we investigated the impact of gas powder two-phase flow on the operation strategies of these kind of storage if they're integrated in the iron and steel industry. And secondly, we investigated the thermal efficiency, which is characterized by the thermocline degradation when the storage is integrated in industrial energy systems. For this purpose, we built two different test rigs. The first one was a cold model test rig to investigate the gas powder two-phase aspects, like research questions were how much powder deposits during charging. The next one was how much powder that was accumulated in the storage in the first place is entrained during discharging with clean air. And we also wanted to know if the accumulation of powder particles inside the storage was uniformly distributed over the whole packed bed or concentrated in some areas. On the thermal efficiency part, we built a hot test rig. This test rig on the left is the diameter of approximately half a meter and is 2 meters high. And there we investigated the impact of the heat transfer flow direction on thermocline degradation and energy and exergy efficiency. So we were interested in the question, what happens if we, instead of charging the storage from the top and discharging it from the bottom, what happens if we charge it from the bottom and discharge it from the top? This was the main research question that we wanted to answer with this test rig. Let's directly jump to the first aspect, the gas powder two-phase flow. In this test rig, we we built this test rig that we can measure the powder accumulation inside the storage, which we did by just measuring the amount of powder that we inserted at the first place, and then the amount of powder that we found in our filters after the packed bed. And with this, we could calculate the amount of powder that was accumulated inside the packed bed during a charging process. And then we also wanted to know the location at which these powders accumulated, and therefore we installed a lot of differential pressure sensors to investigate where the most pressure drop happened during charging with gas powder two-phase flow. Here you see just a P and a D of the test rig. So the results of these investigations were that when charging with gas powder two-phase flow, actually all of the powders that were introduced into the system accumulated inside the system, and the cold exhaust gases that exited our storage during charging were basically clean. And the same happened when discharging with cold air. Basically no powder that was accumulated in the packed bed in the preceding charging process was entrained by the fluids, so the heat transfer fluid stayed clean during the discharging process as well. Considering the second aspect, the location of the powder accumulation, we found that most of the powders accumulated on the top surface of the packed bed, which is the surface at which the hot gas powder two-phase flow entered our system. Here in the plot, you can see the pressure drop on the y-axis plotted over the location inside the packed bed. Basically, this 1 to 3 means is indicative for the upper fifth part, upper 20% of the packed bed, which is the highest pressure loss and therefore also the most powder accumulation. All right. We also took some pictures of our investigations on the top here. The left picture shows the packed bed from a top view after filling the storage. The second picture shows the packed bed after charging with gas powder two-phase flow. So you see that there's a lot of powder accumulated on the top surface. What we did then is we removed the upper part of our packed beds, was approximately 10 to 20 centimeters, and there we found what was already indicated in our data, that the rest of the packed bed wasn't quite as much contaminated as the top surface, which confirmed our experimental data that we measured here. Yeah. To summarize the findings of our gas powder two-phase flow investigations, we found that 98% of the powder deposited inside the packed bed during charging. None of the powder was entrained during discharging, and most of the powder particles that accumulated inside the packed bed were found at the top surface at which the gas powder two-phase flow entered the packed bed. Yeah, that was the gas powder two-phase flow aspects. As already mentioned, we had further research questions, to answer concerning the thermal efficiency of our packed bed storage. There we focused on 2 different operation strategies, which was on the one hand a standby operation, which means you charge the storage once, then you let it sit for a long amount of time, and then you discharge it after, say, 1 day. And the second operation strategy was the partial cycle operation, which means the storage is basically charged to 50% most of the time, and you're just cycling it around these 50% between, say, 40 and 60% in very fast batch processes. So what we found in the partial cycle operation experiments is depicted here. So we did those experiments both for charging from the top and also charging from the bottom. And you can see the experimental results in the plot in the middle. On the left, for charging from the top, the x-axis represents the height of the packed bed, and on the y-axis there's the temperature, both dimensionless. And you can see this S shape is kind of the real life thermocline that you can observe in such a storage. And yeah, the storage was cycled between the solid line and the dashed line. So very fast and short cycles. And on the right side, you can see the same just for charging from the bottom. Of course, the thermocline is then flipped upside down. So you have the hot zone on the bottom and the cold zone on the top, and you're just shifting it by a few centimeters when charging and discharging. We also did those experiments for the standby operation, again, charging from top and charging from the bottom on the left and right, respectively. In the middle plots, you see similar results as before. In the y-axis, the dimensionless height. On the x-axis, the dimensionless temperature. And here in the blue line is the thermocline after charging it to 50%. And after that, we let it sit for 72 hours. And yeah, you can see the thermocline degradation on these green, red, yellow, and gray lines. So let's pick the one for 48 hours. We basically have lost here half of our energy due to losses to the surroundings, which is, of course, yeah, can't be reduced anymore. We see a similar plot on the left-hand side, just again flipped upside down because we charged it from the bottom. In addition to the losses to the surroundings, we also see that, of course, the hot part, which is initially on the bottom, tries to get to the top because of natural convection inside our storage. And therefore, the maximum temperature rises into the middle of the storage, and you have both low temperatures on the top and the bottom, which is very bad for your exergy efficiency because, yeah, let's pick again the red line here. After 48 hours, you charged it from the bottom, and then after 48 hours, you decide to discharge it from the top. You insert cold air from the top, and the hot air on the bottom exits with the temperature of the stones at the bottom. That's just how heat transfer works. So you basically have no temperature gain. You're just shifting the temperature inside the storage and not extracting any energy, which on the other hand is much better if you charge it from the bottom, because then the top layer has the highest temperature in the whole storage. Yeah, to summarize, we found that in partial cycle operation, we didn't see any effect or any differences when charging the storage from the bottom or from the top. On the other hand, we found in standby operation the effects of switching the charging direction from the bottom was quite significant and led to high energy and exergy losses during standby time. So now let me just skip a few slides with too much details and jump directly to the conclusion of our findings. You already saw the findings of our gas powder two-phase flow experiments, and in the thermal efficiency experiments, we found that, yeah, it's already mentioned, the impact of the gas power of the heat transfer flow direction, and we also found that the efficiencies drop by 3 to 5% in the partial cycle operations, and 6 to 7 if the storage is charged from the bottom. And for the standby efficiencies, the values drop by much higher values, up to 18% lower exergy and energy efficiencies if charged from the bottom. So to conclude, we found that our storage does not only act as a thermal energy storage, but also as a dust separator, which is good and bad. We concluded that since the powders accumulate at the surface at which they enter the packed bed, it would be best to charge the storage from the bottom, because then you can use gravity basically to remove the powders from the packed bed. However, we also found that, which is kind of obvious in terms of thermal efficiency, it would be better to charge it from the top rather than from the bottom. So we have two aspects that work against each other. So our idea for the follow-up project was to kind of invent a new storage that can do both these things at one time. And for that, we designed a new configuration of packed bed thermal energy storage, where we just separated the whole volume, which was sitting on top of each other right now. We separated this and designed it in a way that we have two concentric storage volumes, which you can see in this sketch. You basically have a center storage volume here that is filled with your storage material. Then you have a wall, an insulated wall. Then you have an outer part of storage material, which is concentric to the inner part. Again, the wall outside, which is insulated, both sitting on metal gratings. And what you can do then is to charge the storage with hot gas powder two-phase flow. You inject this gas powder two-phase flow from the bottom, enter the packed bed from the bottom as you would like it to separate the dust on the bottom surface. When the dust is separated in the first half of the packed bed, you divert your gas flow, the now basically clean and still hot gas flow, and inject it into the outer part of the storage to charge this part from the top. And yeah, when reversing the flow direction, you use cold air, discharge this part from the bottom. Also flows through the middle part and can be used in downstream processes to preheat stuff or to just generate steam or anything else. So yeah, that's the basic idea we have researching in our new project, if the things the ideas we had actually work in real life. Yeah. That's it from my side. Thank you very much for your attention. If you have any questions, you can, of course, ask them right now or just reach out to me by email. Thank you.
Thank you very much, Paul. Actually, we do have one question in our Q&A section from Gabriele Guastaferro, and she asks, good afternoon, are there on the market PB tests or companies developing it with a current TRL higher than 7 and real applications? That's the first question. And one more from her, why not storing the steam instead of an additional heat storage like PB tests to high volumes, she asks.
Yeah, that are two good questions. For the first questions, I don't think that there are technologies with higher TRL than 7. Up until now, those packed bed thermal energy storage have most of the time been investigated in combination with concentrated solar power to store solar power during the day and use it during night. There are a few projects considering them for waste heat recovery, but they all suffer with or have the problem of the gas powder two-phase flow. So in the field of waste heat recovery, I think we are right now at 5 to 6 TRL. And then for the second question, I'm gonna use this slide. So the problem that we have is that, of course, we already have the steam storage to add flexibility to the steam and water side of our energy system. But the problem that still is there is that on the gas side of the steam generators, there is still no flexibility, and the steam generators are have a high thermal inertia, so they can't follow the excess heat profile of an electric arc furnace, for example, because you have an electric arc furnace, you have approximately 20 minutes of 1400 degrees excess heat, and then you have 10 minutes of no excess heat, and yeah, there are no steam generators that are capable of following this profile, and therefore we need some kind of storage that also adds flexibility to the gas side of our excess heat system. And that's why we are using these packed bed thermal energy storage systems, because we think they are the most robust against this gas powder two-phase flow, as opposed to convective heat transfer surfaces. I hope this was a satisfactory answer.
Thank you very much. We have another one from Christoph Gröchshammer. He would like to know, he says, thank you, very interesting. And he would like to know, did you also calculate a business case, or do you have an estimation of return on invest?
On return on invest, we don't, right now I don't have a good estimation, but we set up an optimization model for our use case, where we optimized first the excess heat system or the waste heat system. This is an existing system of voestalpine at Leoben, Donauwitz, where the waste heat utilization rate was, with the state-of-the-art systems, at 45%, which 1 minus 55% losses. And with integrating a virtual packed bed thermal energy storage, our optimization models yielded a waste heat utilization rate of up to 97%, which is of course an ideal case, but still, yeah, there is a significant increase in waste heat utilization rate, and yeah, that's the result of this optimization model, and hopefully an answer to the question.
Thank you so much. Maybe one last one from me. Do you have actual plans to go ahead in the direction of a concrete demonstration at a steel plant?
Yeah, we actually have. We just started the project where we are investigating the prototype of our new storage that I showed in the last slide. This project is going to last 3 years, where we try to answer still some remaining research questions, like, is the powder separation in this configuration working well? Can we remove the powders in this configuration? There are still some open questions, but if the answers to those questions in this research project are positive, then the next step will be to implement a prototype at our project partner, maybe parallel to the existing waste heat system. But yeah, that's the goal.
Great. Good to hear that you're going forward. Thank you very much, Paul. We now go ahead to our next presentation, and we will continue with the project Recovery Plus, which is presented by Christopher Fritscher from DLR in Stuttgart. Christopher.
Hello all together, and thank you very much for the opportunity to show our latest research results. And thank you, Oliver, of course. My name is Christopher Fritscher. I'm a researcher at the German Aerospace Center for more than 4 years now. At the Department of Alternative Energy Converters, we investigate if it is possible to improve the efficiency by using thermoelectric generators. I studied mechanical engineering, and my responsibilities include structural mechanics simulations, design, prototype manufacturing, as well as experiments on our test rigs. First, I want to start with a short introduction of the German Aerospace Center. We are a big research organization in Germany, and we are divided into 5 activity fields. We provide research and technology transfer to the industry in the sectors of aerospace, energy, and transport. And there are also big interdisciplinary sectors, digitalization and security research. Besides that, the German Aerospace Center is responsible for the planning and the implementation of German aerospace activities on behalf of the federal government. And to the German Aerospace Center belongs also an independent project management organization for research promotion. In these 5 activity fields, more than 11,000 employees working at 30 different locations distributed across Germany, but also in Brussels, Paris, Tokyo, and Washington. Our headquarters is located in Cologne, and I am working from Stuttgart. But now, let me start with explaining our technology. Have you ever wondered where planet rovers like Curiosity on Mars gets its electrical energy from? Because photovoltaics are too sensitive to dust because of its size, it's not feasible. And also batteries are no option because they have a too low capacity for the whole lifetime of such a rover. That's why the solution are radioisotope thermoelectric generators. How does they work? That you can see on the right side. You need heat from a heat source, which is conducted through a semiconductor and dissipated into the environment via cooling fins. In the semiconductor, an electrical voltage is generated directly because of a temperature difference with no moving parts. In such space applications, thermoelectric power generation is already successfully used for more than 50 years now. But nowadays, there are no relevant applications on Earth. I would like to show how it is possible to transfer this technology to terrestrial systems in the next few slides and clarify if it is efficient to use such system for industrial applications. The principle behind this and the reason why it is working is the Seebeck effect. It says if you heat up one side of a material and cool down the opposite side, you get a separation of charge carriers. Such parts we call a thermoelectric lag. You can see it here in the first figure that the charge carriers are moving downward. That's why at the bottom you can see much more electrons or electron holes. And this is the reason why you got an electrical voltage. You only need a serial connection of many such parts and you will get a usable electrical current. Such a serial connection of thermoelectric lags is technically realized in a thermoelectric module. You can see it here in the second picture. In a technical system, you realize the required heat flux with different heat exchangers. Heat is fed into this system through the red heat exchangers. And then the heat is conducted through the yellow thermoelectric modules, which are here the same like in picture 2. And the blue heat exchangers return the heat and provide it for further use. This is called a stacked heat exchanger design. The last figure shows how a prototype of a thermoelectric generator could look like. What you can see is the housing for maintaining an inert gas atmosphere and quite a lot of measurement equipment. All these heat exchangers from figure 3 are located inside this housing. What we are working on at the Institute for Vehicle Concepts is showed here a bit more in detail. You can see the whole process from research of thermoelectric material to the integration to different applications. In cooperation with partners, companies and other research institutions, we investigate suitable material and the fabrication of thermoelectric modules. Our key competence is the designing and developing of such generator systems. In order for the technology to establish itself on the market and for an economic use, we are already looking on how a serial production could look like and the stability of generator systems. In the last steps, we are investigating the integration to different systems for different applications. In the past, we were already able to show the high potential of an economic use in different real applications. The history of the research at our institute is showed here. For more than 20 years now, we are researching and looking on different applications of thermoelectric generators. In the first years, our focus was on car applications. Now we are also looking on commercial vehicles and industrial applications. Overall, we developed a highly integrated end capsule design, and we have done the development of several complete systems. A few of our partners from the past are listed here at the bottom. Here you can see our progress in the last 20 years. I'm sorry for the few mistakes here in the diagram. On the horizontal axis, the years are showed, and on the vertical axis, the power density is plotted. That's the electrical power output in relation to the weight of the thermoelectric generator. Each dot represents a functional prototype of a thermoelectric generator. The ring circles are simulated designs, and the filled circles show real measured results. I think it is really impressive to see that we were able to increase the power density by factor 10 over the last years. This is the reason why now it is the right time for this technology. Now I want to show you one specific application for the industrial waste heat recovery. We have recently completed the research project Recovery Plus, which I want to explain to you now. The goal was to investigate the potential of such a generator at a zinc melting furnace. The heat source is the exhaust gas of a melting furnace, which is operated with natural gas. The technical process parameters are heat flux of approximately 66 kilowatts thermal heat. That means each year we have got waste heat of over 350,000 kilowatt hours. We wanted to make this waste heat usable with a thermoelectric generator. As heat sink, water from the normal heating system was used. So it was possible not only to use the generated electrical power, but also to use the heat. Instead of directly heating buildings for other applications, it would be also feasible to put the heat in a district heating system, or to use a cold absorption machine, or to use it for process heat. On the right side, you can see the design of our prototype and how it was integrated in the production plant system. There you can see also a bypass, which is not necessary. It was only installed to minimize the downtime in ongoing production during the installation of our prototype and for any emergency cases. Here, a few more technical details. The furnace is used for melting zinc ingots. Our project partner, the company Föhl, needed this zinc for the production of die-cast parts. The exhaust gas has a temperature of 700 degrees. Like I already mentioned, this results in a waste heat flow of 66 kilowatts thermal heat output. The furnace has an operating time of more than 5,500 hours per year. So you got more than 368,000 kilowatt hours wasted heat. In the figure on the right side, you can see our temperature measurement for the analyzation of the temperature distribution in the exhaust pipes. This was necessary for developing and designing our prototype of a thermoelectric generator. So how does the generator work here? Of course, the hot side of the thermoelectric modules were heated up with exhaust gas. And like I already mentioned, the cold side were cooled down by water from the local heating network. So more or less, the thermoelectric generator is just an energy converting heat exchanger. This you can see also here on the right side. In the furnace, the process heat is generated. This heat is on the one hand used for the melting process, and the rest of it, so all the waste heat, is carried to the thermoelectric generator. Here, a large percentage of the heat is provided as usable heat for water heating. Another option would be to use the heated water for steam generation or reuse it for process heat. And of course, part of the heat is transformed to electrical power energy. Because it is not efficient to cool down the exhaust gas to ambient temperature, a certain percentage is released into the environment via the chimney. Here you can see a photo of our functional prototype at our test bench. At our test bench, we did an experiment to validate the key figures and to compare it with our design and simulations. On the left side, a hot air mass flow is generated and controlled. At the inlet and at the outlet of the thermoelectric generator, the pressure and temperatures of the airflow were measured. On the top, you can see the blue water pipes, where also the mass flow, the pressure and temperatures are measured. In the generator itself, of course, the generated electrical power and temperatures at 60 different locations are measured. Here are the technical data of our generator design. We reach an electrical power of more than 1000 watts. We provide 37 kilowatts of heat as heating water. The electrical power generation leads to more than 5,600 kilowatt hours per year. And the heat recovery leads to a heat saving of more than 205,000 kilowatt hours every year. That means with the integration of this generator, you can save costs of more than 5,000 euro each year. And the manufacturing costs are less than 5,800 euros. For the calculation of the manufacturing process, we have assumed a production quantity of 100 pieces each year. So we reach an amortization period of much less than 3 years and a reduction of CO2 emissions of over 35 tons each year. And just a little note. In the future, also significant higher electrical power output seems possible. In this research project, we were a bit restricted regarding the availability of thermoelectric modules, and we were able to identify some potential for improvements. Nevertheless, I would say these achievements are quite impressive. And now I want to compare these results with other technologies. For example, for the same electrical power output in 1 year, you would need a big area for photovoltaics, because photovoltaics didn't work at night, or if there are too many clouds. You would need a rectangle of 7 by 10 meters for the same power output. So if you compare it, the size of a thermoelectric generator is much smaller. After testing this prototype at our test bench, we had installed it at the industrial zinc furnace. So we generated real saving of costs and emissions at this company. And of course, it was a research project. That's why we identified further development potential. Here on the right side, you can see a few impressions from the installation. To summarize it and to show the general potential of this technology for future applications. At a water outlet of the generator, we were able to provide a thermal power of 40 kilowatts heat. We reached an overall system efficiency of 3%, if you just look on the electrical power output. And like I mentioned, with a few little improvements, significant higher efficiency up to 6% seems possible, which would result in 2 kilowatts electrical power. Altogether, we predict system costs lower than 4 euro per watt electrical power. Here, just the electrical power output is considered. Providing the heat is an additional benefit, which would improve the system costs. And now I want to compare it to another heat recovery system, the organic Rankine cycle, which is already widely implemented to the industry. The most difficult is that today no systems are available for such small heat quantities. That's why you can see here values for small organic Rankine systems with 100 kilowatts and bigger systems with 500 kilowatts thermal power. The system efficiency for small systems is only slightly higher than the efficiency of thermoelectric generators. For bigger organic Rankine cycles, the efficiency increases. Have a look on the 100 kilowatt systems. If you assume a maximum efficiency of 11%, you would get 11 kilowatts electrical power. But the system costs are quite high, what results in costs of less than 6 euro per watt. For bigger systems with an efficiency up to 15%, you would get 75 kilowatts electrical power. Also here, such systems are quite expensive and big, what results also in costs of 4 euro per watt. So compared to small organic Rankine systems, thermoelectric generators are much cheaper if you have a look on the costs per watt. And even compared to big organic Rankine cycles, the system costs are in the same range like thermoelectric generators. This should show you that thermoelectric generators are competitive to organic Rankine systems. What are the next steps for us? This year, we want to demonstrate the development potential in the laboratory, and for next year, the installation for several prototypes in new pilot plants are planned. This is part of a subsequent project where we want to show the potential of this technology to several stationary applications. Overall, we are open for new collaborations in very different sectors for future research projects. Last slide and a small summary of the key facts of this technology. We developed a thermoelectric generator for a zinc melting furnace. Electrical power output up to 2000 watts seems possible. The cost-benefit ratio is in any case better than €6 per watt. If you look on the generated electric power and the provided heat, we got a payback period of less than 9 months. The experiment with prototype shows really good agreement with our simulations. And my most important message for you, thermoelectric generators are an economic solution for industrial waste heat recovery, especially for small volumes of heat, maybe even for higher amounts. It is the best technology on the market. For any questions, please ask me now, or you can also contact me after the webinar. Thank you.
Thank you very much, Christopher, for the highly interesting presentation. We do have 3 questions in the Q&A, so maybe we can take all 3. We start with the question by Jonathan Gonsalves. Can it be used for variable waste heat? Can it go off and on depending on the circumstances?
Yes, of course it can. The lifetime stability and long-term stability is quite important, and that's why we are looking on it at the moment, because the thermal cycling could be a problem, but it is possible, yeah.
Great,
but it
thank
needs
you.
some further investigations.
Okay, great, thank you.
We are working.
Charles Rand asks, is there a plan to electrify these zinc melting furnaces? And in that case, could electrification lead to stranded heat recovery assets? Like
yeah, we have already contact with several companies, and some of them tries to transform it to electrical heating systems, but there are still a lot of companies which using, like here in this project, natural gas furnaces. But this is also, like I mentioned in our current project, that we are also looking on different other industrial applications where it is too difficult or the temperatures are too high to electrify it. So I think there's still potential for this technology.
Frank Mintus wants to know, thank you very much, very impressive. Do you have long-term results, e.g. is the efficiency changing after several months of operation?
Like I mentioned, we are already working on it, but like I started at the beginning, this technology is already used in space applications for a lot of decades, and there you can see a bit of degradation, but it is not that bad. And now we have to show and demonstrate that it is also possible for terrestrial applications. And this is also the reason, like I mentioned, that we have an inert gas atmosphere in the housings. It is also possible for the future that it is maybe not necessary, but we have to look on it. It also depends on the temperatures you have at the thermoelectric modules. Yeah.
We have 2 questions regarding temperature. Is there a maximum input temperature, or what is the minimum usable waste heat temperature level? Maybe you could elaborate on that.
It depends on the material which you are using for the thermoelectric modules. And also it depends on the design of your heat exchangers. we are normally designing our heat exchangers that we have a hot side temperature of the thermoelectric modules of nearly 500 degrees. But there are also other materials for lower temperatures.
So it depends on the material used.
Yeah.
Thank you very much again, Christopher. It's time now to switch to our last but not least, of course, presentation from Thomas Sanz de Santa Maria. Go ahead, Thomas.
Hello, everyone. Thank you very much for having me, and thank you for my colleagues. All their presentations have been very interesting. Now, I'll introduce myself quickly. I am Tomás Sanz de Santa Maria. I'm a thermal engineer. I'm a Colombian living in Paris, and I have around 10 years of experience in heating and cooling systems. This is me in our factory in Stuttgart in front of our heat pump, or one of our test heat pumps, which I'm going to talk about in a bit. I work for Armstrong International. It's a company funded in the USA in 1900, 125 years ago. And we're a solution provider on thermal systems. And we're also a heat pump manufacturer through our joint venture with Combitherm, which is a German company based in Stuttgart. And today I want to tell you the story of how an ice cream factory is well underway towards decarbonization, and it has proved that industrial heat pumps work. This ice cream factory is in Germany, and if you could see in the ice cream all the carbon that it takes to turn your ice cream into the delicious snack you take, it would look like that. And we want to help them move them towards a greener ice cream. And along the way, they have taken 3 key steps towards decarbonization. The first of them was to fully de-steam their system, and they turned into a hot water loop at 105 degrees. A while ago, they had their steam boilers providing all the heat for their users, and they switched to hot water. This was very important. You're going to see in a while why. Then they also did direct heat recovery wherever possible. This is something every factory should strive for, try to do direct heat recovery in their processes. And the final step, which is the one we're the most proud of because it's the one we helped them do, was to install their first heat pump. And here's an image. It's the red box there next to the hot water tank. And the image on the right is the inside of the heat pump with the compressor. So they installed it about 3 years ago, and about 5 years ago, and it's been running since, and they're very happy with it. But something that triggered the de-steaming, which was the first good thing that they did, was the installation of a combined heat and power system. And many of you might think that this might be a step in the wrong direction. They were going to increase their gas consumption to produce electricity and heat. This would be the Sankey diagram of the system before installing the combined heat and power. They would take in gas, burn it in the boilers to produce steam for their users. And parallel to this, they would get electricity from the grid and use it in their users. And after the installation of the combined heat and power, they increased their gas consumption, part of it to the boilers, part of it to the combined heat and power to produce heat and electricity, which led to a reduction in their electricity purchase from the grid. But something that we need to remember is that in 2008, when this CHP was installed, the carbon intensity of the electricity grid in Germany was very high. It was 525 grams of CO2 per kilowatt hour. As reference, gas has 200 grams of CO2, or natural gas is 200 grams of CO2. So if instead of energy, we look at CO2 emissions, the total site consumption or site emissions were about 13,000 tons of CO2, part of it linked to the gas consumption of the boilers, but a big part linked to the electricity consumption of the grid. After the combined heat and power was installed, the grid consumption decreased, and yes, the gas consumption increased, but the total CO2 emissions were reduced by 39%. And there were some unexpected benefits of installing the CHP. First of all, they de-steamed, because before the CHP, there was steam, and they said, okay, which combined heat and power system should we buy? One that produces steam or one that produces hot water? They noticed that the one that produces hot water has better efficiency because the return temperature of the water reduces the temperature of the fumes. And they said, okay, let's go for it. And there are, of course, some other benefits to it, because when you remove the steam from the system, you reduce part of the maintenance because you have less steam traps to maintain, and the losses due to radiation are less because the temperature of the pipes is less. And another unexpected benefit is that because of the German subsidies that they would get, they were having to shut down the CHP every so often because they had some excess heat that usually it would be used for heating water. And because they were not being able to use all that heat, it would have to shut down. I'm going to explain this a little bit more in detail in a bit. Before that, let's take another look of the other step that they did. We talked about the de-steaming. Now let's talk about the heat recovery. As you can imagine, an ice cream factory demands lots of cooling. At the end of the day, you have to freeze your ice cream. And for those of you who are not familiar with refrigeration systems, I'm going to do just a quick recap. The heart of the system is the compressor, which is absorbing refrigerant, in this case ammonia, from the evaporators. It goes out very hot, passes through the cooling towers, the condensers, comes out as liquid, enters the evaporators again, gets evaporated, and then is absorbing all the heat from the factory. Now, these systems are installed everywhere. In many factories, you'll see them. And here there are three main points where you can recover heat. 2 points which are high, or let's call it medium temperature. The desuperheater, where you take the refrigerant that is coming out of the compressor at a very high temperature, and you can reduce its temperature without starting to condense it. And you can also recover heat from the oil that is used to lubricate the compressor. So these two systems are, let's call it medium temperature heat recovery, between 50 and 70 degrees. And then there's a lot more heat. There's more amount of heat, but at lower quality, lower temperature, which is the condensation of the ammonia. Most systems condense the ammonia with ambient cooling with at around 20 or 30 degrees with cooling towers, but you can also put a heat exchanger and get a water loop at around 25 or 30 degrees. So if we look at it in a Sankey diagram, we expand the one we were seeing a little bit ago. This is how the system looked after they de-steamed with the CHP, but before they increased the running hours with a heat pump. So they had gas going to the boilers, gas going to the CHP, the hot water, the 105 hot water loop provided heat to some high temperature users, mostly the pasteurizers for the pasteurizing the milk that would eventually turn into ice cream, the clean in place systems, and they also had some other users at medium temperature, less than 70 degrees, and part of it was water heating. And some of this water heating was met with the 105 degree loop, but part of it was also with existing direct heat recovery coming from the ammonia compressors, which did their cooling, took electricity, and they had this medium temperature waste heat we just talked about, and all the heat in the condensers, which was of course not recovered. At the time, only a little bit was being recovered, and they also had the heat coming from the last heat exchanger in the combined heat and power, which was the one that sometimes could give heat and the CHP would run, but sometimes if this guy would give too much heat to the water, then this guy would have to turn off, because if it didn't dump this heat, then they wouldn't get subsidies from the German government. So when I first saw this, I thought, well, the most logical solution would be to install a heat pump here and take all the heat so that they don't dump it and they can use it. And this would run the heat pump, the combined heat and power more, and pump up the temperature and inject it into the high temperature users. However, if we had done that, if at some point the CHP were decommissioned, then the heat pump would just run without a heat source. So what we did was this. we connected a heat pump to the medium temperature waste heat. This little line, it looks kind of the same size, but it's slightly smaller here. So we took more heat from here to bump it up in temperature with a heat pump, injected in the high temperature users, and this increased the amount of heat that could be taken from the combined heat and power, and increased the amount of electricity being provided by the combined heat and power, and reduced the electricity being bought from the grid. But you're probably wondering, there's still lots of waste heat available. The site is only needing 1,800 kilowatts. These are average kilowatts, so taking the megawatt hours of the year divided by the operating hours. So on average, 1,800 kilowatts of heating from the boilers and the CHP, and you have almost 4,000 kilowatts of waste heat. The system could eventually run without gas, but we're going to get there in a second. Before, let's ask ourselves the questions. This heat pump was ordered in 2019, so about 11 years after the CHP was installed. Did it still make sense in terms of CO2 to install this heat pump and increase the operating hours of the combined heat and power? Germany had gone a long way. From 525, it went down to 390 grams of CO2 per kilowatt hour of electricity. But if we do the same exercise we did a bit ago, we see that the current operation with CHP still has less emissions than if we had switched to only boilers. Only boilers would make an increase in CO2. Very little, where the carbon intensity is going down in such a way that it's very close to not needing to run. And in fact, this is what happened recently. The factory established a green power purchase agreement, making now their grid electricity 0 grams of CO2 per kilowatt hour. With this, it doesn't make environmental sense to keep running the CHP and keep burning more gas. Economical sense, that's another story, because electricity prices and gas prices are what would drive this decision. And now that this electricity is greener, we could turn off the CHP, and the way we set up the heat pump, it can keep on taking heat from the ammonia coolers and not the CHP, so it could continue to run. And we can now install more heat pumps to fully decarbonize the site. So going back to how we're running today, before decarbonizing in the future, we have it like this. And our proposal to the site is to move to this. Isn't this beautiful? No black gas lines, only electricity, green electricity. And so the electricity would come, feed the ammonia compressors, which do their cooling as they have to, provide the medium temperature waste heat and the low temperature waste heat. We keep on running the heat pump we already installed. We would install a new high temperature heat pump, almost the same characteristics as the existing one, which would take the medium temperature waste heat it needs to provide the remaining heat for high temperature needs, pasteurization and everything. And we would also install a medium temperature heat pump that would take, of course, electricity, the medium temperature waste heat, but the available medium temperature waste heat is not enough for all the medium temperature needs. It would need to take some of the low temperature waste heat, which is at less than 30 degrees, which is why the COP of this heat pump is not as good as the one from the high temperature. High temperature is at 4.5 and the medium temperature is at 3.7. And still, there is still lots of waste heat available. If the site wanted, it could eventually add another medium temperature or high temperature heat pump and sell the excess heat to a district heating system or something like this. Now, let's zoom in a little bit on the heat pumps themselves. And let's talk about their technology and their operating limits. This is what we call the operating envelope for our heat pumps. We have several, but two main working fluids. We work with HFOs. And this is the R1233. which is capable of reaching 120 degrees in the hot side, but it can only cool down to around 35 degrees in the cold side. So this is the operating envelope it has. This is the temperature of the heat source, and this is the temperature of the heat sink. The high temperature heat pump we saw in the example previously would be operating around here. It was producing 90 degrees water, and it took as source water at around 60 degrees. The medium temperature heat pump is operating around here. It was taking water at around 25, 30 degrees because it had to tap into the low temperature waste heat, and it was producing 70 degrees water. The COP, something moved a little bit here in this graph, but I'm sorry about these weird lines. It was not like this in my presentation. So ignore this diagonal lines. This is the COP of the heat pump, depending on the leaving water temperature and of the condenser, the hot part, and the leaving water temperature of the evaporator, the cold part. So, as you saw initially, the site was working with a 105 degree hot water loop. So if we had wanted to produce 105 degrees here, 105 degrees, with the source that we had, which was around 60 and 45, we would have a cup which is not that good, around 3.7. But because we targeted the temperature users directly, which were 90 degrees, we could move the COP all the way over here. So produce 90 degree water, still with the same source, but now we were operating at around 4.5 COP. For the medium temperature heat pump, we had a similar situation. We could have produced 90 degrees and feed everything with a 90 degree hot water loop, but we chose to target, or we're choosing to eventually target directly the users that are less than 70 degrees, which allows us to increase the temperature, I'm sorry, not the temperature, the COP to 3.7, with sources between 30 and 15. And it's a shame that this diagram is not the one I have, because the one I have has dashed lines for the 1, 2, 3, 4 refrigerant and solid lines for the other one. So yeah, something went wrong here in the passing from one part to the other. Now, this factory in particular didn't need steam, which made things a little bit easier. But if the site had needed steam, we still offer a solution to produce steam with these high temperature heat pumps. As you saw in the previous slide, our heat pumps can reach up to 120 degrees in the condenser. And if we take this 120 degree water and we pass it through a steam evaporator, we can produce low pressure steam up to 0.7 bar. And if we need higher pressure than that, we can pass it through a steam compressor, a mechanical vapor recompression system. We don't make those. We make the heat pumps and the steam evaporators, but we work closely with some third parties to integrate the mechanical vapor recompression and go up to 180 degrees Celsius steam, up to 4 tons per hour. So in conclusion, this factory now knows firsthand that these heat pumps works, have these heat pumps running for 5 years, and they're making gas savings and allowing their heat pump, their combined heat and power to run more. But each factory is different. Careful engineering needs to be done for correct integration. Sadly, we and I have seen in other factories heat pumps that were bought, but since they were not correctly integrated, they were just not running. And another point, ice cream is not the only place where these heat pumps can be implemented. I'm going to show you a couple of examples where we've installed them. Cargill, which produces food for fish, for salmon, in Norway, they integrated our heat pumps in their dryers. They have to dry the food. And there's a really cool video on YouTube. If you look for it, you can see a little more information about this project. But basically, they're taking the exhaust air from their dryers, which comes out humid and hot, well, still hot, and they need to heat it up usually with 120-degree water. So we took the exhaust air as a source. We cooled it down with a 50 and 40-degree water loop. And so then the condensate would then go out a little bit colder into the atmosphere. The heat pumps then would consume a little bit of electricity and bump up the temperature in this hot water loop at 120 degrees and be used to dry the food. Another integration we did was in a pharma company that they needed to heat up their water for injection. Water for injection is the water that ends up in these little bags that you might get in your IV. And as you can imagine, this needs to be very sterile to avoid any possible infection in the patients. And they need to keep it very hot at around 95 degrees to avoid any possible contamination. They also have chillers on site used for cooling the production rooms. So we took the excess heat from those chillers, from the condenser of those chillers, fed it into our heat pumps. They installed 3 of them here, and it produced the hot water to keep the water for injection circuit hot. So we have several installations. Here are just a couple of pictures. Each heat pump integration, it's their own story, and all of them are very interesting. We, of course, have the control system in the heat pump, and the control system can be integrated into the factory's SCADA or management system. So you can remotely turn it on and off, change the temperature set point so you can run at better efficiency. Eventually, you could also do thermal storage when you have cheaper electricity on the grid, make the heat pump run at higher temperature, and when the electricity is a bit more expensive, run it at lower temperature. But that's another presentation. And in general, we have more than 100 heat pumps worldwide. We have a factory in the US, which is being built. We have built one in Mexico. We have a factory in India and in China. And we're building a factory in Belgium. There's already the original factory, which is running in Stuttgart. And this 100 heat pumps is equivalent to 50 megawatts of heating power installed. The average capacity of each of the heat pumps is around 700 kilowatts. And they've been installed, as you saw recently, in many different industries: food, pharma, labs, district heating. And we've been doing this for more than 50 years. About a quarter of the heat pumps installed operate in the high temperature regime, which is from 95 to 120 degrees. And that's it from me. Thank you very much. And now I'm open for your questions.
Thank you very much, Thomas. We do have some questions in the Q&A. We start with Gabriele, who wants to know if you have considered type 2 absorption heat pump, and is there a particular reason for choosing electric heat pump in that case?
Type 2 electric heat pumps, type 2 absorption heat pumps, also known as heat transformers, are great when you have a lot of waste heat and at very high temperature. And I hope I'm not confusing it with type 1. But from what I remember, they're very good when you have a lot of waste heat and at very high temperature, and you're only needing some heat at a lower temperature. Or was it the other way around? There was the other one, which is if you have very high temperature heat, but you're willing to split it. You can have very high temperature or medium temperature, split it, and then use a little bit of it in the high temperature. Yeah, I think that those are the ones that are heat transformers. I don't use absorption heat pumps often. I often get them confused, the type 1 and type 2. But for this application, using a type 2 would waste a big part of that already waste heat. You could bump it up with that and it wouldn't consume electricity, that's true. But there might not be enough waste heat to run it like those. And also, from what I've seen, don't have a lot of experience with absorption heat pumps. They're not very regulatable. They're not so easy to run at part load. Our heat pumps have variable frequency drives on the compressors, and we have several compressors per heat pump. So it's very easy to stage them off and run at different loads. Of course, we also try to dampen it with thermal storage. In the picture I saw you, there was a 100 cubic hot water tank, which also helps with this. But that would be the main reason why I wouldn't use, or we didn't integrate an absorption heat pump here. But I'm sure there are applications where it would work very well.
Thank you. We have another one from Rodrigo. He wants to know why not using natural refrigerant fluids. Is it only because of efficiency? And what about the F-gas regulation?
Right. For natural refrigerants, we have CO2 and we have ammonia and propane. So propane, we really don't want to use them. These are explosive, so this is something we would avoid at all costs. This is an internal decision. We've said, I know some companies are doing it, but we wouldn't want to install a heat pump with the risk of exploding at some point. Ammonia is toxic as well, and to run at these temperatures, it needs very, very high pressures. The highest temperature I've seen an ammonia heat pump run was 89 degrees. When you want to go above 90 degrees with ammonia, you have to go transcritical, and that brings us to the same issue with CO2. CO2 also runs in transcritical, which means that the delta T in the condenser must be very large. You exit at high temperature, but the return temperature must be very low in order to take all the heat coming in the dry cooler, as we call them in CO2 systems. So CO2 systems are usable in domestic hot water because usually you're coming in very cold and then you need to bring it up to a high temperature. So you have the large delta T. But in this factory in particular, we have a hot water loop that has a regular delta T of around 10 degrees. So you need to have supply 90, return 80. And with CO2, that is just not feasible.
Okay, thank you. We have one last one from Micha Heinrichs, and I think we're now talking about economics. Are there measures in place regarding how large the difference between gas price and electricity price should be in order to transition to the green future scenario?
Yes, that's a good question. And I did think in this presentation to put some more economics into it, but I thought we would stay on the technical side. But in general, the spark spread, the ratio between the electricity price and the gas price should be less than the COP of the heat pump in order to get financial savings. And in 2008, I think, or 2019, the spark spread in Germany for this factory was around 4. So electricity was 4 times more expensive than gas. So it absolutely made no economical sense to install a heat pump because the COP was 4.5, so it was very close. But this has improved. Germany is now moving closer to spark spreads of 3, 2.5, 2, which make these type of projects much more attractive. The lower the spark spread, the closer the electricity price is to the CO2, the more attractive economically these projects are, and the faster the payback will be. And there are actions in place that will happen soon. There is the ETS 2, the European trading system, which currently only affects high emitters like steel factories or cement factories. But these smaller industrials like ice cream are not affected to pay for the CO2 they emit. But starting 2027, the ETS 2 will come into effect, which means that all these smaller industrials will also have to pay for the CO2 associated to their gas consumption. So gas prices will increase and the spark spread will decrease, making these projects more feasible.
Great. I think this is a very important message at the end, that we are going into the right direction regarding that thing. Thank you again very much, Thomas. We have now reached the end of our webinar. Thank you once again to all of our speakers for your great contributions, and to all of our participants for your interest. I hope everyone enjoyed our second webinar. As a brief outlook, the date for the third webinar has not yet been set, but it will take place in approximately 3 months. And the topic of our next webinar will be digitalization and AI for industrial energy efficiency. Thank you all, and goodbye.